Good morning. This is the first presentation, the introduction to the Midwest OpenFOAM Users Group. My name is Dan Combest. I'm from MW, and this morning we're meeting at Washington University in St. Louis. So just an overview of the meeting this morning. Our objective is to discuss the need for a users group and to introduce OpenFOAM to new users, because I know that there's several that are here. The topics that are going to be covered today are overview of the users group, OpenFOAM in general, kind of cutting edge applications, and then we'll end on today's agenda. First and foremost, I need to give a disclaimer and say that this presentation, this users group meeting, this offering is not approved or endorsed by OpenCFD Limited, the producer of the OpenFOAM software and the owner of OpenFOAM and OpenCFD trademarks. If you want to find more information about OpenFOAM, you can go to the OpenFOAM Foundation website at www.openfoam.org. Beginning with the overview of the users group, today's attendees, we have several universities that are part of the users group. Some from University of Iowa, CRB, Washington University, St. Louis University, and then I'm from MW. Today we actually have about 25 attendees for those listening. We have several speakers, some from Washington University, some from University of Iowa, and then we also have Dr. David Gayton speaking from the United Kingdom this morning. The purpose of a users group in general, and the purpose of this users group, first and foremost, to promote the application and development of OpenFOAM based technology. Specifically, geographically there's different users group meetings in the US and around the world, so this one is for the Midwest. So we want to promote the application and development of OpenFOAM based technology. We also would like to organize local meetings and offer a venue that is within driving distance of each other, and then be able to share these technical presentations related to OpenFOAM. Third, we want to provide basic training to new users and connect experienced users to discuss advanced topics like optimization or programming or fluid mechanics or how to tie in third-party libraries, just kind of advanced usage and application of OpenFOAM based technology. The next one would be connecting group participants to discuss 1. Collaboration on academic and or industrial projects. There are numerous users group meetings around the world where a lot of the users will collaborate with each other. They share code, they work on the same projects. This day and age, you need to work with other people, and sometimes you need to convince your PI to let this happen. But in the end, there's different groups with different expertise, and ultimately everyone wants to get publications, everyone wants to get funding for their groups. Some universities have more resources than others, and maybe you have a great idea and you need to collaborate in order to make that great idea happen. And number 2, employment opportunities for students. So it's a great place for students that have done some great project to present their work, to talk about their work, to talk about their struggles and how they came through and really solve these problems, and to have companies that maybe would or can relate to these problems that are being solved and say, hey, I need to hire this guy. Reduce the cost of employment. You don't have to, or finding employees, you don't have to pay for headhunters or anything like that. It's much easier if you come to these small groups and you can meet people and have firsthand experience of what they're doing. And last, sharing cutting-edge research related to computational fluid dynamics. So I said CFD, but it could be computational continuum mechanics if you have some great structural solver or discrete element method or something. This is a great place for you to just talk about it, and somebody may be inspired by you, or maybe you can pass your project on. A lot of times projects can be one and done, but if we share them, you might be able to collaborate and your work can go further. So the other users group meetings in the US, the first and foremost, probably the one that is met the most, is the Mid-Atlantic OpenFOAM Users Group meeting. It's organized by Eric Patterson of Virginia Tech. So far they've hosted 5 meetings. They have lots of industry that shows up, different universities that show up, and they provide basic training. The next one that I've attended is the New England OpenFOAM Users Group meeting. It was organized by 2 graduate students and hosted at the University of Massachusetts in Amherst. Their first meeting was last year in 2013. They provided basic training. I was fortunate enough to go there and be able to give some training. Overall, the meeting was very well organized. They did a great job. So if they ever have it again and people are in the region, it's a great place to meet other users and also share your own work. The next one is Pacific Northwest OpenFOAM Users Group. I haven't actually seen a website or any comments. It might just be very small and have just a few attendees, so I would keep an eye out for them. Internationally, there are several, there's numerous users groups across Europe and through Asia. The Dutch OpenFOAM Users Group meeting. In Sweden, there's lots of users. Australia, and then different parts of Germany, north, central, southern parts of Germany. There's just a lot of OpenFOAM users in Europe in general. And there's also many more in Austria and China and India and Israel and Russia. There's just too numerous of users group to list them all right here. OpenFOAM is an acronym for Open Field Operation and Manipulation. It started development in the 1990s as foam at Imperial College in London, primarily by Henry Weller and Herb Yazek and others. In 1999, Nabla Ltd. Was founded to commercialize foam, and in 2005, OpenFOAM was actually released by OpenCFD Limited under the GPL, and it was the first publicly available code repository. Now there's 4 notable forks that are active in the community. There's the standard version that's put out by ESI and OpenCFD Limited. There's the Foam Extend version, which is on SourceForge. It's kind of regulated and headed up by Wiki Limited. Then there's a version called Helix that's put out by my company, Engis, and this one is Linux and Windows versions. And then finally there is a version put out by the company Blue Cape called BlueCFD, which is a Windows-based solution. OpenFOAM is an open source CFD library for solving problems in computational continuum mechanics. So I put CCM in here because it's a broader area of application that includes CFD. So there's Lagrangian libraries, there's structural libraries. People have created adjoint solvers and optimization code from this. So CCM is a broader terminology for this. So kind of an example of this, of OpenFOAM and its power, the canonical OpenFOAM example is the representation of partial differential equations. So if we take this simple transport equation for a scalar C, the C++ code, the top level code that would represent this is shown here. We have time derivatives, we have divergence terms, we have Laplacian terms, we have source terms. And within this, there's inherently implicit, explicit terms. There's differential operators. The code is tensor aware, so it knows that I'm transporting a scalar rather than transporting velocity or transporting momentum or transporting Reynolds stress. The code is aware of these different representations, these different fields. And also there's encapsulated numerics. So behind all of this, there's discretization schemes, there's different linear system solvers. So it's all encapsulated away from this. Also, OpenFOAM is a method or a library that's based on the finite volume method with polyhedral mesh support, arbitrary polyhedral mesh support. So it works with mesh cells that are any shape. OpenFOAM is a collection of utilities and solvers in a single simulation environment. So what do I mean by utility and solver? A utility is a standalone application that you use to pre-process or post-process. This includes mesh generation or data analysis, things like that, anything that you would need to prepare a case, and a case being the collection of boundary conditions and mesh and just everything that you would need to begin a simulation. And a solver is a standalone application that simulates a model or models. So for instance, incompressible isothermal turbulent flow. There's a special solver for that. If it's steady state, then we would use something called SimpleFOAM. Also, OpenFOAM has a coding structure, a class structure that provides easy model-model interaction. So not only here we can see we have div phi u, so that's the divergence term inside of a transport equation, but the next term is turbulence. So this is a interaction of our transport equation with our turbulence models. And then the last line right there, FE options, is actually a source term that would be related to u. So something like multiple reference frames, or if you had porous media or something like that, would interact with this transport equation with the FE options. Next, the code is separated and structured to have various levels of abstraction. So different components of OpenFOAM can be worked on separately. They can depend on each other, but they're compiled separately in a way that they don't necessarily have an effect that one will not, they don't have such an effect that when you change one thing, the entire library has problems. For instance, FE options, we can add these on the fly. We can add different source terms. It's actually some of the newer functionality that's come in the last 2 years, or last year. It's actually very nice for multiple reference frame and porous media flow. And then it is a library that is fully parallel through a domain decomposition method. So what do I mean by domain decomposition method? Actually, what we would do if we want to parallelize this on a cluster is you take your computational mesh and you would physically break it up into different regions. And so for this one we have 1, 2, 3, 4, 5, 6 different regions, and each one of them are run on a different node, and they communicate with each other to provide seamless integration, seamless calculation of this answer. So on the left is actually the decomposition, on the right is the final answer. So each processor is in charge of a spatial region. The communication is done via MPI, and you can do optimal decomposition. So how do you break these domains up? Well, you can do this using other libraries like Scotch. So the code structure of OpenFOAM. So the installation folder consists of 2 main directories. The first one is third party, so these are non-native components. There's external libraries, MPI, compilers, ParaView, anything that you would need that's not necessarily within a Linux distribution or Windows distribution that you would need to compile or run OpenFOAM. The next one is the OpenFOAM applications and libraries. So it's in a folder that's like OpenFOAM-2.3- release -x or something, whatever. And the first number is the OpenFOAM base platform version. The second number is a maintenance release, for example, 1, so 2.3.1 or 2.3.0. So you'll notice that there's differences in each one of these versions. The OpenFOAM library has several main subfolders. The first one being application, which holds all of the source code and of the utilities and solvers. Bin, which holds executable scripts for OpenFOAM components. Doc, it's the original documentation for OpenFOAM, so there's a user's guide and a programmer's guide and some Doxygen files, which will help you figure out the class structure and how the classes are related to each other. etc are configuration and settings files. Lib, it's where the program library binaries live. Source are it's the core of OpenFOAM, so it has the actual program library's source code. Tutorials, coincidentally, it's actually the tutorial sample cases for various solvers. And then wmake is the very nicely done compilation system for OpenFOAM. OpenFOAM has a growing level of documentation within the code, so every year there are more comments within the code. With each new edition, there's more comments that you can go and read if you're actually going through the code itself. The code is separate, so it allows for separate customization, so you can write your own linear system solver or your own discretization scheme and not really have to worry about how that will necessarily affect the incompressible flow solver or volume of fluid method. It is structured in a way that allows simultaneous work by multiple people, so OpenFOAM or foam extend is built by contributors from around the world. So there's different groups that will provide code and submit code to be part of the extend project. So because of its structure, it allows for this simultaneous work. Also, there's something called dynamic loading. So it allows you to kind of drop code in at runtime. You can make your own boundary conditions without necessarily having to recompile the entire library. You can pull out components and load at runtime. And the compilation of code, once you've compiled the entire library, if you want to make your own code or make your own solver, the compilation of the code merely requires linking of libraries and linking of the headers rather than an entire recompilation of everything. So wmake does a good job with this organization. I wanted to talk about some of the more cutting-edge applications. The first one is the simulation for offshore wind farm applications by Matt Churchfield and Sang Lee of NREL. They have done a great job of using OpenFOAM and created a toolbox to model wind farms. They're able to capture wake turbine interactions, wake atmospheric boundary layer interactions, wake-wake interactions. They have topic-specific workshops. They have a workshop. It's been the last few years. I went to it this past year, and it's very good. There's lots of great presentations. They've done a good job with their code, and I think they're only gaining more momentum. So it's a great project to contribute to. And they actually provide their code at GitHub if you're familiar with the Git system. The next application area that I wanted to talk about was the continuous adjoint optimization. Here we have an example of continuous adjoint that is applied to topology optimization and surface optimization. So on the left, the topology, the domain itself is morphed to achieve an optimal based on different objectives: flow uniformity, pressure drop, swirl. Each of these can be combined. There can be porous media, there can be multiple reference frame. So this particular one on the left is kind of a generic example. On the right, we have an example of continuous adjoint optimization applied to a surface. So we can use this for external aero to morph the shape of an object to do things like reduce drag or improve downforce. So this is a great example of that. The next application that I wanted to talk about was Swag for Foam. So it's a collection of tools, different boundary conditions, Groovy BC, function objects, different source terms. There's Python integration, there's different utilities. Funky set fields is a great utility that if you're using InnerFoam, which is a volume of fluid solver, but funky set fields is a great way to initialize domains. The next one is PyFoam, which is also developed by the same person. You can use PyFoam to control runs, manipulate data, set up cases, change boundary conditions. If you like Python, it's a perfect integration between Python and OpenFOAM. And here are the two addresses for Python or PyFoam and Swag for Foam. If you just Google those two words, you'll find everything that you need to know. The next notable application is an implicit block-coupled solver developed by Dr. Mangani and Darwish. It is a methodology that couples pressure and velocity solving simultaneously rather than sequentially. So it's different from a segregated approach, which we'll talk about this afternoon with a discussion about simple and PISO. This is a methodology that couples pressure and velocity, and it can solve up to 15 times faster than a segregated simple approach. It's extremely robust and stable, and it is competitive with commercial codes. There's some presentations out there which compare the work by Mangani and Darwish with other commercial codes. The last one is a finite volume based solid mechanics solver. There's lots of people working on this. Dr. Philip Cardiff is kind of the main guy, or one of the main guys, and his work was focused on modeling the stresses inside of hip joints. He's been presenting at the OpenFOAM workshops for the last few years, and he always produces, great work, great numerics, gives a great presentation. So if you do have a chance to go to an OpenFOAM workshop, which next year it will actually be, in 2015 it will be in Michigan. So I strongly encourage people, if they can, to go to this conference. And kind of a notable aspect of this is that the solid mechanics are done with finite volume instead of finite element, which is a little different than what solid mechanics is normally solved with. It's a extremely active project. It's part of the Foam Extend project, and right now they're trying to leverage the block coupled matrix, so the block coupled functionality that was in the previous slide. They're trying to use something similar to solve these solid mechanics equations, and there's a tremendous opportunity to contribute. So if people are looking for projects, I think this group of people, there's a lot of things that can be done, or applications that can be looked into. So it's a great project to be part of. Today we have lots of really great talks. So in the morning we'll have a few from some students at Washington University, and then also Dr. David Gaydon, who did his work at the University of Manitoba. Later in the morning we will have some talks on optimization. Dakota is another library that a lot of people use with OpenFOAM, so Tim Ray is going to talk about this. And then we'll have a very nice presentation about the volume of fluid algorithm in OpenFOAM itself. And the last one, Eugene soon will talk about gas-solid modeling. So if you're familiar with Euler models or modeling gas-solid reactors, this is a great talk to listen to. And then finally, this afternoon, we'll have some training. There'll be I'm going to do an advanced introduction to CFD, so kind of talk about the finite volume method. We'll have a little bit, a very detailed presentation on simple and PISO algorithms, and then we will have kind of a hands-on, if you've got your computer, by Eugene's son, and then finally we'll end on some coffee and just sit around and talk. Maybe we can go around and talk about each one of our projects, and then we'll have some concluding remarks by Eugene.